Everyone. Welcome to this week's Crunch seminar. And today we have two speakers from Crunch Group, and each will give a paper review on the recently published paper. So our first speaker is Dr. Shengze Cai, and he will give us a paper review with title Simulating Continuum Mechanics with Multiscale Graph Neural Networks. So let's welcome Dr. Shengze Cai.
Okay. Do you have my slide?
Yes, we can see that.
Okay. Yes. Thank you for the introduction. And yeah, today I'm going to present this paper where a graph neural network is used to simulate the continuum mechanics. And the authors are all from the Imperial College London. And this paper was recently published last month on arXiv. Let me first give an overview of this paper. And the author proposed a multiscale GNN model, which denotes a multiscale graph neural network to simulate the unsteady continuum mechanics. And the idea is simple. So given an input field U at the initial time step, and a single evaluation of the multiscale GNN returns the flow fields at the next time step. And by applying the model recurrently, we can simulate the continuous systems for a long time. And this model is based on the graph neural network and is trained by using supervised learning strategies. Okay. This is simple, and there have been a number of related works in this topic. So obviously, the traditional numerical solvers are well developed for the simulations, and they can achieve high levels of accuracy, but may be computationally expensive. And recently, there are some machine learning methods developed for the simulations. And most of the learning-based methods focused on the convolutional neural networks, namely the GNNs. And the GNNs have advantages in translation invariance and locality. However, the GNNs require the input and output fields to be defined on rectangular domains represented by regular grids. So it's not very suitable for the complex domain. And on the contrary, the graph neural networks are more flexible. And the graph neural network can be designed to satisfy the spatial invariance and locality as well, but the domain can be discretized as unstructured sets of nodes. So recently, there are some works using GNN to simulate physics problems. And among these references, it's worth taking note of the work from DeepMind. So in these 2 years, they use GNN to simulate both fluid mechanics and solid mechanics problems. So the paper I'm presenting today follows this work, and the authors proposed to use multiscale graphs, and they also consider periodic boundary conditions for the continuous systems. And they also consider a technique called adaptive graph coarsening and refinement. And the model will be applied for 2 examples. One is the advection problem, and the other is the fluid mechanics problem. Okay, so let me first recall some background knowledge of the graph neural network. So this is a typical graph. And in general, a graph contains 2 key components. One is the nodes, and the other is the edges. And the edges can be directed or undirected. So for example, in this figure, we can see an edge connecting 2 nodes have some specific directions. So we call this directed graph. And each dielectric edge connects a sender node denoted by S and a receiver node denoted by R. And more importantly, we should note that each node or each edge can be assigned a vector of node attributes or add attributes. So in general, the node attributes encode the features of the data, and the edge attributes encode the relationships between these elements. So these are some basic notations of the graph. And a graph is used to represent the data. So after building a graph, another important question is how to learn something from the graph data. And in other words, how to update the attributes in the graph. So people use a layer called neural message passing. So assuming that this is an input graph with the initial representation of the data at each node, and the output of the MP layer is still a graph. However, the information of the nodes and edges have been updated. So
hi, Shengze, excuse me. Just I have one quick question. So the communication between the two nodes is only one way, or it can be two way?
Yeah, it can be bidirect. Yeah, it can be two way.
So the B can send the information back to A?
Yes, yes.
Okay, thanks.
Okay. Yeah, so the functionality of the MP layer is very similar to that of a convolutional layer or a dense layer. However, the representation of the processing data is very different from the others. And here are more details about the message passing. So MP layer can be divided into 3 steps, including the edge updates, the aggregation, and the node updates. So for the first step, we use a function FE, which is parameterized by a neural network, and it takes the edge itself and the sender node and the receiver node to update the edge. So taking this as an example, there are 2 edges in this graph, and after the first step, we can have the update edge attributes, E prime here. And here, E23 prime is computed by this. And in the second step, we summarize the edge information from all the neighbors by using a function low. And low must be a permutation invariant. For example, it can be average or summation. And for example, in this case, E3 bar is the average of these 2 edges. And finally, we combine the edge information and the current state of the nodes by using another neural network to update the node information. And here is the example corresponding to the V3. Okay, so the MP layer can be summarized.
Shengze, what is the second step? E3 bar means what?
Means all the information sending to node 3, node number 3.
Oh, so that's actually an edge node interaction.
Yes, yes. So this, So this vector summarizes all the information sending to the same node.
Oh, I see. I can see that in 3. Yeah.
Yeah.
Right. In 3, it's E bar, ER bar. Yeah. Okay. Yeah. Okay.
Yeah. So all the message passing layer can be summarized by these equations, and one graph neural network can be composed of 1 or more MP layers to update the information in a graph. Okay.
And here, when you have FE, which is a neural network in the step 1, and then FV is another neural. These are standard feed-forward neural networks.
Yes, or it can be convolutions. So these are defined by the users.
Okay.
It also depends on the data structures. If this is images or some other type of data, it can be convolutional neural network.
Yeah.
Yeah, so, okay, now let's go back to the model proposed in the paper. So as we mentioned, the idea is given an input field U, a single evaluation of the multi-scale GNN returns U for the next time step. And the domain is discretized into a final set of nodes, V. And each node, the position of each node is defined by X. And in addition to the nodes, which are the mass grids used for the CFD solvers, and we should also create the edges. And in this paper, the edges are created by connecting a node with the K nearest neighbors. And K is also a parameter determined by the users. Okay, so the important thing is what are the node attributes and edge attributes to represent a physical field. So in this paper, the node attributes is a concatenation of 3 components, where U is the investigative fields and P is some physical parameters. For example, it can be the Reynolds number in the fluid mechanics problem. And omega is the mask of the Dirichlet boundaries. So if the node is located at the Dirichlet boundary, it can be omega is 1, otherwise it's 0. And in the for the edge attribute, it denotes the relative positions between the sender node and the receiver node. So this is how they represent the physical fields into a graph.
Shengze, how about the pressure? The pressure is not part of the node in the Navier-Stokes, or
yes, this can be several fields. This is
okay. Because if it's a multiphysics, then that contains all the parameters there. And also the graph is stationary, right? The xi is constant. It's not moving, right? All the xi's.
Yes.
Okay.
But they have another technique to update the positions after the evaluation of the graph neural network.
At this point, what makes it multiscale? Because I don't see anything on multiscale, or it's coming up.
It's in the next slide. Here. So, the authors claim that if we only use one MP layer or only use a few MP layers, you can only propagate the node and edge information locally between the neighboring nodes. However, some physical systems require propagation at large scales or even globally. So they suggest to use a multiscale architecture of the graph neural network. So this is the architecture used in this paper, where G1 is the original high resolution graph, which means that it includes all the nodes. And G2 is a low resolution graph created from the original graph. And the nodes are few. It contains fewer nodes. Okay. So this looks very similar to the UNet structures. However, there are 2 questions here. One is how to generate the low resolution graph from a high resolution one. And the other one is how to communicate between the high resolution graph and the low resolution graph. So this may be easier to implement in the convolutional neural network, but for the graph neural network, it's not very straightforward to achieve. So they do the following things. First, how to build a low resolution graph from a high resolution one. So this is an example. We have the unstructured nodes distributed in the domain D, and these nodes are denoted by V1. And we want to create a sparse node, sparse graph. So for the first step, we divide the domain into a regular grid with cell size dx by dy. And for each cell, provided that there is at least one node in V1, we add one node to the low resolution graph. So here we have 4 nodes in this cell, and we add one node here. And this node is called parent node, and these 4 nodes are called child nodes. And the coordinates of the parent node is the mean position of this child nodes. And on the other hand, provided that there is at least one edge from this cell to another cell, then we add an edge to the to V2, which is the low resolution graph. So by doing this, we create an independent graph which has fewer nodes and edges. And let's come to the next question, how to communicate between the high resolution and low resolution. And previously we set
Can I ask a quick question here?
Yes.
Okay. So if the grid is too fine, that might not contain any node. If this is the case, then how do they handle? They just create a random node?
You mean like in this region?
Yeah, for example, if the grid size is very small, so that there might be a potential grid rectangle that doesn't contain any node. Then if that is the case, then they just, so did they explain how to do that?
In that case, you don't need to add any nodes in the new graph.
I see.
So yeah, so the principle is that at least one node in a cell, then you need to add a new node. Otherwise, you don't need to add anything.
Thank you.
Okay, so now we have the parent nodes created from the child nodes, and we create edges connecting the child nodes and the parent nodes. So with the edge attributes assigned as the relative position between the child and the parent nodes. So we create these edges. And we also use another neural network to process the data from the high resolution graph. And by using these equations. And after that, we assign the node attributes to the new node for the low resolution graph. So this is called downward message passing layer, and there's a new neural network here. And similarly, we need to pass the information upwards. So we create the same edge as the downward message passing, and use this equation to update the node attributes for the high resolution graph. So this equation takes the information of the edge and the node attributes for the low resolution graph and the high resolution graph to update the node attributes. So this is how they handle this multi-scale structure. And there are three key components here we just introduced. Okay. And because the multi-scale GNN will be applied to the physical problem, so the author also consider to impose the periodic boundary conditions. So this is what they do. And they use a transformation to transform the spatial coordinates from this to this. And some of us may be familiar with this because we also have similar operations for pins and dipole nets. And the idea is the k nearest neighbors algorithms for creating the edges will be applied to the transformed coordinates. Because if we apply the KNN algorithms to these coordinates, we will not have connection between the nodes at 0 and the nodes at P. But if we apply the KNN algorithms to these coordinates, these two nodes will be connected. And there will be an edge between these two nodes. And the edge attributes are assigned the relative positions between nodes in the original coordinate system, except at the periodic boundaries where P is added or subtracted. So this is how they handle the periodic boundary conditions. And finally, let's see the loss function used to train the model. And we mentioned that this is the supervised learning strategy. So we have ground truth data for training. Here, U denotes the ground truth data, and U hat is the prediction from the neural network. And the loss function is composed of three terms. The first one is the mean square error of the field at the original nodes. And the second one is the mean absolute error at the nodes on the delusionary boundaries. So this is used to penalize the delusionary boundary. And the third term is the MSE for the rate of change along the edges. So to my understanding, this is to penalize the gradient of the field or the flow field. And there are two weighting coefficients in the loss function, and they choose these hyperparameters here. And it's a bit surprising to me that they didn't add the third term for the fluid dynamics problem. They set lambda E 0 for the fluid dynamics problem. Okay, another thing is how they train the model. So it is reported in the paper that each training iteration produces a single time step. And then every time the training loss decreased below a threshold, they increase the number of iteration steps by 1 up to a limit of 10. And this is not very clear. If I understand correctly, they do the following things. So the input is U at TK, and after a single evaluation of the GNN, they get U at TK plus 1. And this will be used in the loss function. And after training for some time, they increase the number of evaluations. So now they have also the prediction at TK plus 2. And both of these will be used in the loss function. And the number of evaluation increase gradually up to 10. So this is how they train the multi-scale graph neural net. Okay, we have introduced the model, and now we can go through the training data and the results. So in order to train and test the model, they generate the data using Nectar++. And the first example is for the advection problem. So this is the equation, and phi is the scalar field transported by the velocity field. And they generate a number of data sets, and only 2 of them are used for training, and the rest are used for testing. And the differences between the training sets and the testing sets are twofold. First, in the training data sets, they only consider uniform velocity fields. And in the testing data sets, they also have non-uniform velocity fields. And second, in the training data sets, they only consider a square domain or a rectangular domain. However, in the testing data sets, they have several different geometries. And there are 4,500 simulations in total for training, and each of them contains 50 time steps. So we mentioned that the node attributes includes 3 components. So in this problem, in this advection problem, U is the scalar field, and P includes 2 velocity components. So they assume that the velocities are known. And the graph neural network is used to predict the scalar field from an initial time step to a future state. And another problem is the incompressible fluid dynamics problem. In this case, they consider the Navier-Stokes equation for the flow past a circular cylinder, and they generate the data for different Reynolds number. So for training, they generate the data at the Reynolds number from 500 to 1000. And for testing, they generate 3 different data sets for different range of Reynolds number. And each simulation contains 100 time steps. And in this fluid dynamics problem, the velocity and the pressure fields are the solutions we are interested in. So U includes U, V, and P. And this P denotes the Reynolds number. Okay, so this is the data set for the fluid dynamics problem. Now let's show you some results of this paper. The authors mentions that despite the multiscale GNN being trained on square or rectangular domains and uniform velocity fields, it can be generalized to complex domains and non-uniform velocity fields. This is due to the unstructured data representation for the graph neural network, so which makes the model independent to the geometries. So here are 2 examples. The first one is the Taylor-Coet flow, and this is the domain. The inner and outer boundaries rotate at different speeds, but in the same direction. So we know there is a shared flow for this problem. And we can see that the multiscale GNN seems to capture most of the structures compared with the ground truth. However, we can see the scalar field is a bit diffused, as shown in this figure near the boundaries. So the error at the last time step is relatively large. And they also try to assess the qualities of long-term predictions, where they use the model to predict 99 time steps of the simulation. And in this case, there are 3 cylinders inside the domain. So we can see the evolutions of the flow, and they found the MAE increased approximately linearly along time. So when the simulation comes to 99 time steps, the absolute error is actually very large. We can see the color bar here. The maximum error is about 1.25. It's over 50% compared with the ground truth. 50% relative error compared with the ground truth. And this is the results for the incompressible fluid dynamics. And the movie here shows the simulation for Reynolds number 700, and which is in the range of the training data set. And even though we can observe that the error increased a long time, and at the last time step, the error is also very large. Okay, play again. And the figure here shows the MAE over 99 time steps for different Reynolds number. So we can see in the interpolation region, the model performs well. However, it provides much larger errors outside the range, which is reasonable because the extrapolation is always a challenge for this data-driven methods. Okay, so this slide shows a parametric study for the multiscale graph. And in this table, we can see they use different levels, different multiscale levels. And they provide the MAE for the last time step and the mean value over all the time steps. So we can see for the advection problem, we cannot observe significantly improvement if we compare the L equals 2 and L equals 1. The reason is for the advection problem, the information is propagated only locally and at a finite speed. So the multiscale architecture doesn't help here. However, on the contrary, the multiscale setup is very important for the fluid dynamics problem. And as shown in this table, if we compare L equals 2 and L equals 1, we can observe significantly improvement. The error is much lower than here. The reason is the incompressible fluid have a global behavior due to the pressure. The pressure wave travels at an infinite speed. So the multiscale, the low resolution graph will help to learn the characteristics and achieve much lower error here. And at the end of this paper, they also introduced a technique called adaptive consonance and refinement, which is used to increase and decrease the spatial resolution of nodes before every model evaluation. So basically, this algorithm increased the nodes where the gradients of the flow field are high and decrease the number of nodes if the gradients are low. So in particular, they compute the gradients of field at each node by using this equation. So you first compute the difference between the nodes and its neighbors, and then average all the differences to obtain the gradients of each node. And if the gradient is lower than a constant, we need to remove the k closest nodes for this node. And if the gradient is higher than another constant, for example, this red, this node color in red. So we first triangle this node with the neighbors, and then add a node in the center of this triangle. So they use this to refine the mesh. And we should note that the nodes on the boundaries are not considered in this technique. And they also claim that by using this technique, we can get an improvement with 11% reduction of the MAE. Okay, that's all the results they have in the paper, and let me give a brief summary. And in this paper, they proposed the multi-scale GNN, and there are some advantages. So the first one, they can divide the domain into unstructured nodes, which is more flexible for the complex domains. And they use multi-scale graphs to capture high and low resolution mechanics. And they consider periodic boundary conditions. And finally, they use adaptive coarsening and refinement technique during the evaluation of the GNN. And there is no doubt that for the data-driven methods, the inference is much faster than the CFD solvers. Yeah, so that's all for this paper.
Thank you very much, Shengze, for this presentation. Is there any other questions for him?
Shengze, I have a question on the adaptive refinement. So here, isn't this expensive because they have to regenerate all the coarser graphs, or is that's not so expensive?
In their paper, they report that each evaluation takes about less than 100 milliseconds. But I'm not sure if the evaluation includes this refinement or not.
Yeah, because if it's not expensive, then I was thinking how we can use this for Lagrangian methods, right? Like for the molecular dynamics that we're talking about. Because if you were to recreate the multiscale graphs every time step, that would be expensive.
Yeah, but I think so. If we add a new node or remove a new node, we have to retrain the network, right? Oh, because the network architecture is changed. It has to be retrained. I'm not. Is this correct?
No, they didn't mention to retrain the neural network because they said that the neural network trained after training, the neural network is independent to the node structures.
I have a question for Zheng. Because you see the error in time increases, right? Very fast, the 100 time steps. Is there any way to put some structure, like symplectic structure, let's say, in the, what they call it, the MLP, the what's the layer? That layer that advances from one to the other, one time step to the other, so that we bound the temporal error somehow. Because the method overall has good elements, actually. It's just that you don't want in 100 time steps to explode in time, the time error.
Yeah. One thing I can come up with is like maybe, let me think. So maybe, I'm not sure. Like maybe what in the output of the graph network, you don't output the next. I mean the state variables at the next step directly. Maybe you can output the like the right how to say the right hand side of the equation and use a symplectic solver to make the to do the integration in time. I'm not sure if that would work in this case.
I see. Yeah. Yeah, because you get to du dt equals f. You want the f basically.
Yeah.
From the graph.
Mm-hmm.
Okay, I have one question.
Yes.
Yeah. Is that did the paper give intuition of why the use of MSE and MAE are in the loss function?
And no.
There's no intuition behind that.
Yeah, I have the same questions during when I'm reading the paper, but they didn't provide any explanation on this.
Okay. Thank you.
Shengze, I have another question. So did the author mention any like general advantage of using graphic neural network to solve this problem, comparing with other network in terms of like accuracy or efficiency? Yeah,
the main advantage is the data can be unstructured nodes. So if you use CNN, the data will be interpolated to a regular grid. But if you use graph neural network, you don't need to do any interpolation. You can directly use the mesh grids here.
Okay. So how about compared to DeepNet?
Yeah, I think DeepNet can also do this as well, but I'm not sure.
Okay, thanks.
Hi, Shengze. I also have one question. Is the boundary condition in the training data only one set or different sets? I kind of forget. Like, do they have different sets of boundary conditions for the training data?
Yes. So the training data can be periodic boundary condition. So for the first one is periodic, and for the second one, it's only periodic in one direction, and in another direction there's a dirichlet boundary condition.
And
So
for the for the dirichlet, it's a fixed value, right?
Yes.
Okay. So then after using this, like in the box region to train this network, they mentioned that they can transfer this result to other geometry. Is that what? Okay. Yes, because if this is the case, then it seems that the network is learning the local interaction independent of the geometry. But it seems that the number of different geometry and or boundary conditions is still very small. Like they only have like one is periodic in two directions, one is periodic in one direction and dirichlet in the other direction, and also only with one fixed value. So yeah, I'm kind of confused why this can be transferred directly to different geometries. Because intuitively I think that the number of boundary conditions or the shapes are not that large, so that so that it can be flexibly transferred. Do you have any idea of that?
Yeah, this is a good question, and I think the reason is during the training they don't use any information of the positions. So they only consider the relative positions between the nodes. So it will be, so it will not affect the testing examples. I'm not sure.
Okay, yeah, thank you.
Hi, Shengze, can I ask a question?
Yes.
Yeah, so you mentioned they has some recurrent features for their network. Is that something that they specifically use to ensure the long-term?
But here the recurrence is not about the network itself. So the network is only trained to take one time step and predict one time step. And they they evaluate the network to by using this as input to predict the next time step. So it's a bit different from the recurrent neural network.
Okay, so it's after the training they.
Yeah. So after the training, in the testing time, they use the initial step as the input and predict time equals 1, and then use this as the input again to predict time t equals 2. So they are using the same network to do long-term prediction.
But after, for the second time step, for example, will the network be updated?
No, in the testing stage, no, it will not. And in the training, as I mentioned, so yeah, so yeah, in the training, they gradually increase the time steps, but the network is still the same. We need the input is always 1 step, and the output is always the next time step. So, and in the LSTM or other recurrent neural networks, we usually have multiple time steps as the input.
Right.
Yeah, but this is not the case they are using.
Okay. But how do you think they can still maintain long-term quality, good quality of their inference?
I think benefits from this training strategies, but actually the long-term prediction is not very good in this paper.
Okay.
So there's still room for improvement.
Okay. Thanks.
And Rui, I was wondering if this is a good candidate for solid mechanics problems.
Mm-hmm. Yeah, let me see.
Because the deformations are not as big as, it's not like in fluid where.
Yeah, so you mean solid
along.
mechanics is more Lagrangian than the fluid, which is usually Euler.
Right.
Yeah, let me see. I think probably this is a good way, like using graph neural networks. Yeah, as an alternative method. Yeah, I think so.
Yeah, and in these papers, they actually use graph neural network to simulate the solid mechanics.
Mm-hmm. Okay, so the figure is another paper.
Yeah, from DeepMind.
Mm-hmm. Okay.
Hey, Shengze.
Yeah.
Can I ask a question?
Yeah.
I'm wondering whether the periodic boundary condition is a requirement for this scheme in order to generalize for different geometry. Because I can understand if the boundary are periodic, even those nodes at the boundary, we still can consider them like in an inner domain. So such that if the scheme can preserve some local structure, then yeah, it can generalize to other geometry. But I'm just wondering whether this is a requirement.
Yes, for example, in this case, there is periodic boundary condition in both directions. So the graph should connect this boundary with this boundary, so they can communicate with each other during the evaluation.
Okay, so
I'm not sure. Yeah.
But does they use the chain model for using this chain model for other geometry? Do they have any example for that?
No, these two testing cases are the geometries of these two cases are different from the training data sets. So for the training data sets, they only considered an open area in a square domain, and there's no other objects inside the domain.
I think Shengze is right. In the training, the periodic boundary condition makes it like local interactions.
Yeah, yeah.
And then on the testing, but see on the testing, they impose the Dirichlet boundary conditions, right? For the cylinder, for example.
Yes.
So only a testing, because they have this term. The loss function you show us is, can you show us the loss function again? The loss function is for the training loss, but how about during testing? Don't they impose the boundary conditions?
No, but in order to create the graph,
because there's no cylinder there, there's no boundary in here. How does the boundary come in? It has to come through the boundary conditions.
You mean the Dirichlet or periodic?
Yeah, Dirichlet. Well,
yeah.
The training stays there. The training is like that square, right?
Mm-hmm.
Like you said, the add box on the top. And then they take the different domains like you have on the right.
Yes.
The geometry would come in through its attributes.
Mm-hmm.
And if I have, let's say, a zero boundary condition on the boundary, how would that be imposed? It has to impose that testing time. Because at training, you don't know the geometry.
Yes. Yeah. Yeah, I don't have a good answer for this.
But Shengze, what's going on during testing? I understand the training, but during testing.
Okay, during testing, for example, you need to provide the graph at the initial time step, right? So the input is a graph at the initial time step, and a graph includes this information.
Okay, so you know the boundaries then.
Yeah, but you know where is the boundary, but I'm not sure.
Right, so how would the boundary condition be imposed?
Yeah.
Like the flow past the cylinder for the cylinder. Or the three cylinders.
Yeah, that's right. So they only have a mask for the boundary, but not the exact values.
Yeah, is there any other questions for Shengze? If not, let's thank Shengze for giving this presentation, and thank you very much again. And yeah, now let's welcome our second speaker, Dr. Liu also from Crunch Group, and he will give a paper review with title Machine Learning, the Kinematics of Spherical Particles in Fluid Flow. So Liu, can you share the screen, please?
Yeah, sure. Let me try.
We are seeing the presenter of, okay, yeah, no, that's correct.
Okay,
yeah.
okay.
Yeah. Please speaking, yeah.
Okay. Hi everyone. So today I'll present a paper review for this article named "Machine Learning the Kinematics of Spherical Particles in Fluid Flow." So it's a work from the SAPIS group published in 2018. So the problem that they are interested in here is that for inertial particles suspended in fluid of, for example, in density rho f, and in considering a 2D inflow, incompressible flow problem with velocity u x t, and Lagrangian particle velocity actually can be described by this Maxi-Rayleigh equation. This equation where the R here is basically a density ratio between the fluid particle density, the fluid density and the particle density. And epsilon here is a inertia coefficient that describes how much inertia effect this particle has, described by the Stokes number as well as the particle density ratio. So for this specific equation, the epsilon has to be much smaller than 1. And Stokes number is defined as this. You can see basically is from the Reynolds number, but also considering the particle sizes. Here, ddt is a material derivative. Here, if consider inertia effect coefficient goes to 0, then the equation basically describes a motion of a ideal passive tracer. So note that here the particles are actually non-interacting with each other. In 2008, these two people actually came up with a reduced order model of this MR equation, solution of this MR equation. Basically, they show that this particle velocity can be can equal to the fluid velocity plus certain higher order terms. So this model is compared to the MR equation, it obviously it's a much simpler equation that is essentially is a kinematics model, because we don't have the second order terms anymore. So it only requires a local flow field. However, this equation has limitations when the epsilon basically the particle inertia, the flow inertia becomes sufficiently large, or when the fluid velocity gradients in time or space becomes large, then this equation would fail. Examples are, for example, when you have unsteadiness and also you have vortices in the flow field. So this work, they're aiming to basically develop a new model that combines the leading order slow manifold approximation, as we see in the last slides, with a data-driven part, as you can see here in this equation. Basically, here the G term here is the part that they are aiming to learn from the data. And here, basically, the input of this G term is actually a time series. And here tau is basically a time lag parameter, P is the sequence length. And this C here basically is a four-dimensional vector that contains the fluid velocity, the local fluid velocity, and also the local gradient of the velocity at the particle location. So the training strategy that they have is such here, as you can see on the left. Basically, they're employing the standard LSTM recurrent neural network to learn this VD. Basically, is the difference is the correction that would make their reduced order to be closer to the MR's exact solution. And here in this in this framework, basically, they have LST here, and also they have a dense neural network connecting the output from LSTM to this VD at the output layer. And during the training, basically what they were doing is that they were basically getting, once they get this output from this basically the model velocity, particle velocity, they combine it with the reduced order velocity, and then compare that velocity with the exact velocity obtained from the MR's solution. And once they got this new particle velocity, they basically march the particle to the next time steps, and where they will have a new fluid field velocity, fluid velocity around the particle, and they basically then feed this turns back into this series, the time series, to the recurrent neural network. So some specific of this machine learning architecture is that they have the LST layers with 128 hidden units, and the dense forward neural network has 64 hidden units, and they're using ReLU activations connecting the output layer. And for the training data, basically they're directly integrating the MR equation with a prescribed flow field, which they treated as ground truth. So they're using the gradient-based add-on optimizer, and the loss function is defined basically as they were trying to optimize, they're trying to minimizing the model, the RN network output with respect to the ground truth. And there's a weighting factor. Basically, they had start with a W0, which is a relatively small number compared to 1. And then after certain time steps, they are changing to a larger weighting factor. So the idea behind this is that they want to get rid of the initial errors where the difference of the model is, the error of the model is much larger than afterwards. So so they first apply this this hybrid model to learn a cellular flow. So basically considering a two-dimensional cellular flow model describing by this equation here, basically it tells the basically the string function can be described by this equation, and then once they got this string function, they can calculate the flow field. And for this specific problem, as they will show later, even though they start with a small epsilon number, which is the particle inertia, since there's a large spatial and temporal derivative in this velocity field, there's still a difference between the particle and the flow velocity, which makes their hybrid model necessary. So so in this model, basically they during the training they apply a unit. They basically start with this A, B, and omega, these coefficients as a uniform distributions, and they randomly assemble those A, B, omega terms in this for this equation, and then train their data. During the training, there, as we said before, this inertia return actually is small, and this particle density ratio is 1.55. So they got 1,000 trajectories by solving the MR equation, and they obtained a long time series that is 1,500 time steps, with each time step of 0.002. And after training, they claim that their loss function can be as small as 3 to the power -3 after 300 epochs, and which is much smaller compared to the leading order equation error compared to the ground truth. So on the right-hand side, basically shows this flow field, the figure A here. Figure B here basically shows that there is indeed a difference between the particle velocity and flow velocity, even though this particle inertia term being small. And they were showing that the difference between the particle velocity and the leading order term is also pretty significant and somewhat in phase or has certain correlation with the difference between the particle and velocity and the fluid velocity. So here, C and CDE, they basically showed that using their strategy, they were able to correct the leading order solution to a solution that is closer to the ground truth. So here, in all those figures, basically the orange curve is the leading order solution, and the black trajectory here is the ground truth, and the blue trajectory is the result from their hybrid model. And it's also interesting from D and E that you can see for the leading order term, they actually start initially they are actually fairly good, but it only deviates drastically after a certain time step. And it seems like what the hybrid model was doing was basically behaving better in the longer time step. And in the next case, basically, they were applying their trend model, which was trained from the previous cellular flow directly to this flow over cylinder case without a relearning procedure. So in this case, for this problem, the Reynolds number they were picking was 250. So then you will have vortex shedding in the downstream of the particle. And their model results was able to achieve the mean squared error of 0.08 over 50 test cases with 550 time steps, which is comparably small from the leading order error. And on the figure on the right hand side, basically on the top row, basically shows the particle trajectory, as you can see, where the blue curve is basically the result from the hybrid model, and the orange curve is from the leading order solution. And seems like the difference is small actually from this particle trajectory. However, if we look at the figure C and D, which is showing the particle velocity in X and Y direction with respect to time, we can see that the hybrid model indeed was able to behave better in terms of the amplitude of the velocity fluctuation in over time in both X and Y direction. So lastly, they apply their trend model to a 2D turbulent flow case. I think this case is very standard here. So they are solving basically this equation using the pseudo-spectrum method with 128 Ferri mode. They retrained the model still from the cellular flow case, but with a smaller A range from 10 to 20. Previously, I think it's from 10 to 50. And they didn't really give a reason why. Probably was trying to capture the smaller scale, smaller. And here are some of the results. So basically, overall, their mean squared error was able to achieve 0.09 compared to 9.88. So here they were showing some quantitative numbers. Basically, they showed first the probability density versus of the particle velocity, particle fluid velocity difference, and you can see that their model was actually better compared to the leading order term. And coming to the figure B and C, basically B, they're showing the autocorrelation function of the particle velocity with respect to the frequency. And as you can see that their model was able to capture this more higher frequency fluctuations compared to the leading order approximation. And in the Paul spectral density, again, their model was able to behave better. So here are showing some basically the flow field where you can see those red dots are the particles, and those particles tend to be attracted to the vortex. And as you can see, the top row is the ground truth, bottom is the prediction from their hybrid model, and it seems like they were able to show good comparison between the two. So conclusion, they have developed a—
Leo, can you go back? If you look carefully, let's say at T.2.8, 2.8, right?
Yes.
If you look at the upper right corner and elsewhere, you will see that not the same.
Yeah. So
even in the naked eye norm.
Right. It seems like yes, that's a good point. So I think it might be because
also inside the vortex, the vortex on the right, just outside the vortex, you see there's like this. Yeah, there's all these other particles that were predicted that they were trapped in the vortex. You see there? There's like 4 particles, but only 1 in the outer spiral. Yeah, there's like, yeah, there. Yeah. that's not good agreement.
Right. So I think because
there only has one particle inside that branch, vortex ring, but there's only 4. So at later times, the deviation is big. So.
Right. Yeah, I think because also their training data was based on a simple cellular flow, and for this case,
you said you relearned it from here. Or you relearned it?
No, they relearned from again a simple cellular flow instead of this turbulent flow.
Oh, I see.
Yeah, but they were choosing a different smaller range of the A value, basically the smaller fluctuations. The amplitude is smaller. Yeah, but I agree that in those outer side regions where the vorticity is relatively small, I think they are not behaving as good. Yeah, so just summarize what they have done. They basically developed a blended model-based machine learning approach for describing the motion of small spherical particles in fluid flow. And I would say it's really just for non-interacting particles. And this proposed hybrid model basically combines a analytical solution with a LSTM RN machine learning model to basically complement the analytical leading order approximation, so that they can improve the overall accuracy. And they showed that their kinematic model constructed from particle trajectories in a relatively simple flow field, namely the cellular flow case, they can actually further successfully generalize to a more relatively complex flow with no additional readjustment. So showing some of sort of generalization. So I have some comments and I guess critique, and I would welcome more. So basically, I think their approach, unlike pings, for example, where the physics is directly embedded as a regularizer during the training, I think their model basically combines the physics and the data in a more separate manner, I would say. And I was asking, like, what is helping the generalization? Is it because they are using the reduced order model that is helping the generalization? So I think to better demonstrate this, to better answer this question, I think they should also compare their results with those from the pure data-driven results without the trained with the LSTM, but then without the ROM. Then we could compare this, adding physics, how would it help? And lastly, I think it's, so this paper actually, there are a lot of places it's unclear, like in terms of the technique they developed. And for example, and also the robustness, for example, they didn't discuss how the change of, for example, sequence length and time lag would affect their model sensitivity and robustness, which I think probably involves a lot of fine tuning. So yeah, so that's all. And thanks.
Yeah, Leo, thank you very much for your presentation. And is there any other questions for Leo? By the way, Leo, do you think, although they don't mention the whether RM helps the generalization, do you think that works given the size of their data set? Do you think that is helpful?
I think ROM is helping in a way. For example, they start from this cellular flow, so then as basically try to learn the difference between the leading order approximation with respect to this ground truth solution for this flow. And then basically the difference is tuned in a way that has certain connection with the leading order approximation. And then since this structure is somewhat representative, then they were able to go further beyond and to some other different cases. And they were, I think, specifically showing the flow structure where it's somewhat like the cellular flow structure. Like they didn't show somewhere else, for example. I was actually thinking maybe those places it would be off. And similarly here, in this case, so we just mentioned, I think, like where there's no vortex, I think in general, the comparison or its behavior might be diminished. But yeah, really, I wish they had they have showed more results to give us more insights for why this worked.
Yeah. Okay. Thank you very much. Is there any other questions? So everyone have a good weekend and see you next week. Bye-bye.